All readings or measurements taken from a measuring instrument are subject to uncertainties. Uncertainties arise when the quantity that we are measuring does not fall exactly on the scale reading of our instrument. Take, for example, the length measurement that we have here. We can see that the edge of the object is approximately at 5.6 centimeter. But how sure are we that the edge of the object is exactly at 5.6 centimeter? It could be slightly more than that, or it could be slightly less than that. As a result of this, it is often useful to state our measurement with its uncertainty, which suggests the range of values within which a measurement is likely to lie. We commonly state it as the absolute uncertainty, which tells us the maximum range in which the reading is likely to lie. On a measuring scale, absolute uncertainty is estimated to be half the smallest division. In our example here, we can be very sure that the edge of the object will not exceed half the smallest division above or below 5.6. In our case here, the absolute uncertainty is plus minus 0.05 centimeter, as indicated in our figure here. When you want to express a measured value x with its absolute uncertainty, you will tend to write it in this form: x plus minus delta x. When you first look at the symbol delta x, you may have thought that it refers to the change in x, like you would have learned in maths. This is not true here. It actually refers to the absolute uncertainty in x. That is the correct meaning of the symbol here. When writing your measured value with its absolute uncertainty, there are two rules to follow as written here. The first rule is that the absolute uncertainty must be expressed to one significant figures only. And then the second rule to follow is that the measured value must always have the same number of decimal places as its associated absolute uncertainty. So in summary, when you're writing your measured value with its absolute uncertainty, first make sure that your absolute uncertainty is at 1 SF only. And then secondly, make sure that your measured value has the same dp as your absolute uncertainty. Other than absolute uncertainty, you have two other kinds of uncertainty, namely fractional uncertainty and percentage uncertainty. Fractional uncertainty is just you taking the absolute uncertainty divided by the measured value itself, whereas percentage uncertainty is the fractional uncertainty multiplied with 100% to change it to percentage form. As mentioned earlier, absolute uncertainty must only be expressed in 1 SF. However, for fractional and percentage uncertainty, you can express them up to a maximum of 2 SF. Moving on to the examples shown in the table here, you have a measured length of 2.05 plus minus 0.05 centimeter. As mentioned earlier, if you have your measured value expressed in this form, this value that you have here is actually the absolute uncertainty. So over here, the absolute uncertainty is delta L equals to plus minus 0.05 centimeter, whereas the fractional uncertainty is equals to delta L over L, giving us 0.05 divided by 2.05, which in the end gives us 0.024. And then the percentage uncertainty, as mentioned, is actually just the fractional uncertainty multiplied by 100%, change it to percentage form. We have 0.024 times 100, giving us 2.4%. In our next value, we have I equals to 3.04 plus minus 2% ampere. Notice that the uncertainty here is slightly different because there is a percentage symbol attached to it. When you have a percentage symbol attached to your uncertainty, it is not talking about the absolute uncertainty. Instead, it is actually referring to the percentage uncertainty. So your percentage uncertainty here now is 2%. delta I over I times 100% is 2%. Now, when you want to change it to fractional form, delta I over I, you just need to take 2 divided by 100, you will get 0.02. And then when you want to get the absolute uncertainty delta I, you will just make use of the expression from fractional uncertainty here, where you will just say that delta I over 3.04 equals to 0.02. So in turn, delta I is going to be plus minus 6.08 ampere. But recall that I told you that absolute uncertainty must be at 1 SF only. So this one will become plus minus 6 ampere. For our last example, express these measurements with its uncertainty to the appropriate number of SF. Recall that earlier I mentioned that when expressing a measured value with its absolute uncertainty, there are rules to follow. The first rule is that the absolute uncertainty must be at 1 SF only. The second rule is that the measured value dp must follow the dp of the absolute uncertainty. You need to follow the first rule first before you move on to the second rule. Over here, we have length equals to 10 plus minus 0.1 centimeter. We can see that the absolute uncertainty is at 1 SF, 1 dp, whereas the measured value has no dp. Looking at the SF of the absolute uncertainty itself, it's already at 1 SF, so it's really following the first rule. However, looking at the dp of the measured value and the absolute uncertainty, we can see that they do not match. We need to match the dp's. So the correct way to have written the values with its uncertainty would be 10.0 plus minus 0.1 centimeter. So right now, we can see that the absolute uncertainty has 1 SF, 1 dp, whereas the measured value has 1 dp. This is now following both rules. Next, we have mass equals to 2.5742 plus minus 0.024 kg. We can see that the absolute uncertainty over here is in 2SF, 4 dp. Looking at the SF here, we can see that it is no longer following the first rule. So we will need to rewrite the absolute uncertainty here in 1SF, giving us plus minus 0.002. So right now, we will have 1SF, 3dp. Moving on to the second rule, we can see that the measured value over here is in 4dp. Recall that I mentioned that for the second rule, your measured value dp must follow the dp of your absolute uncertainty after having followed the first rule. So since your absolute uncertainty over here is in 3dp, it follows that the measured value must also be rewritten in 3dp, giving us 2.574. Now we would have 3dp over here. By writing them in this form, we would have followed both rules. The last two examples do not have any decimal places to work with. For example, volume equals to 4,783 plus minus 25 centimeter cube. The absolute uncertainty here is in 2SF, but having no dp. Under the first rule, the absolute uncertainty must be written in 1SF, giving us plus minus 30. So now we have 1SF, no dp. In the process of changing it to 1SF, we were actually rounding it up to the nearest 10. Applying the second rule here, we can see that the measured value has no dp too. So how will we go about in applying the second rule when there's no dp to work with? The key here is to match the rounding of our measured value with the rounding of our absolute uncertainty. Over here, we have actually rounded the absolute uncertainty to the nearest 10. So our measured value would need to be rounded to the nearest 10 too, giving us 4,780. Lastly, area equals to 3,891 plus minus 340 millimeter square. The absolute uncertainty over here is in 2SF, but having no dp. According to the first rule, this needs to be written in 1SF, giving us plus minus 300. So now we would have 1SF, no dp. In the process of rounding it up to 1SF, we were actually rounding it up to the nearest 100. When we want to apply the second rule here for the measured value again has no dp. In cases where there are no dp's to work with, recall that earlier I said that you need to match the rounding of your measured value with the rounding of your absolute uncertainty. So over here, we were actually rounding it up to the nearest 100. The measured value here will need to be rounded up to the nearest 100 too, giving us 3,900. We need to round up to the nearest 100. When expressing uncertainties for values that do not have any decimal places, one way to work around them is to purposely re-express the given values such that they have decimal places. For example, volume equals to 4,783 plus minus 25. You can re-express them as 47.83 plus minus 0.25 times 10 power 2. We can see now that there are decimal places to work with. The absolute uncertainty is in 2SF, 2dp. So if we were to follow the first rule, this needs to be expressed in 1SF, giving us 0.3 and 1 dp. Now, following the second rule, since the absolute uncertainty is in 1 dp, the measured value needs to be expressed in 1 dp too. So our final answer is 47.8 plus minus 0.3 times 10 power 2, which is actually the same as before. Lastly, area equals to 3,891 plus minus 340. It can be re-expressed as 3.891 plus minus 0.340 times 10 power 3. Now with the decimal places here right now, we can see that the absolute uncertainty is in 3SF, 3dp. According to the first rule, this needs to be written in 1SF, so it will be written as 0.3. It is now 1SF, 1 dp. According to the second rule, the measured value must follow the dp of your absolute uncertainty. So this needs to be rewritten in 1 dp, giving us 3.9. Again, you can see that the final answer is 3.9 plus minus 0.3 times 10 power 3, which would in turn give us back the same answer as before.